Okay, let's go ahead and get started. Do a quick try this. If you want to stop the video and try it on your own and then come back, you can. If not, just keep watching. Okay, and so on the first one, we've got an aldehyde reacting with potassium cyanide and acid, followed by H3O+. Okay, first step here is going to be, remember that this goes together to make hydrogen cyanide. Hydrogen cyanide is a carbon nucleophile for our alcohol. So we end up with the nitrile attached, right? So we get the nitrile doing addition, and then second step, we get hydrolysis, right? That's what the H3O+ is doing. So we've got our OH, we've now added a carbon, and that becomes the carboxylic acid. Okay, so we get a alpha hydroxy carboxylic acid here. In the second one, we're going to react our carbonyl, the ketone, with this dithiol. First step, that's going to give us the cyclic thioacetal, sulfur. And then in the second step, we do a reduction. Right? And so we actually remove that thioketal and add the hydrogens. So we've reduced, the process here is we reduce that all down, okay? All right, what we're gonna look at today is we're gonna look at Wittigs, and then we'll look at Baeyer-Villiger reactions, and then just start to get into synthetic strategies. So we looked at Wittig reactions on Tuesday in the last class. So if you remember, we had a carbonyl. If we take that carbonyl and react it with a phosphorus ylide, what happens is you get substitution of the ylide carbon to where the oxygen was, giving us a carbon-carbon double bond. Okay. So very useful, right? Carbon-carbon bond forming reaction. So make sure that you keep this one at the top of your memory, right? This is the Wittig. And in most cases, like in this case, it's symmetric, so we're not gonna have to worry about symmetry. But if we do have non-symmetric, so if we take benzaldehyde and react that with this ylide, right? The preference for this is going to be the Z form. And the reason that this is preferences the Z form, right, is that if we look at our phosphorus ylide, and we look at the two sides of this, didn't give myself enough room. Remember that we have the zero ion, the one where it's charge separated. We get the negative, right? This one is not stabilized. So when we have a Wittig, the ylide, where it's not stabilized, then Z is going to be favored, right? So not stabilized, we're going to be favoring the Z. That's different if we use, again, we start with benzaldehyde here, if we use a stabilized ylide. So if I do something like this one, then what I'm going to end up with here is the E form is going to be favored. And that E form is favored because now I'm dealing with a stabilized ylid. And so show that, all right, we've got the phosphorus. Then that can go to our Zwitterion form. We have the negative, right? But then that can be localized, so the oxygen goes up. And so this ylid is stabilized. So we can have different stereochemistry. If we have an unstabilized ylid, right, we're going to end up with the Z, the cis or the Z. And if we end up with the stabilized, we'll end up with E. The other option we have is the Horner-Emmons reagent. I'm sorry, the Horner-Wadsworth Emmons. So this is like the Wittig, except now what the reagent is going to be is I'm changing the phosphorus as well. So instead of just being 3 phenyl groups around that phosphorus, for the Horner-Wadsworth Emmons reagent, we have a phosphorus with oxygens attached, and we have the stabilized, right? So now we have a stabilized. So if we use this reagent, we now have stabilized that. And we will get the E form. And now for this one, for this type of reagent, it's always going to favor the E. So most often you'll see Wittigs used with unstabilized ylids giving Z, not always, but often. And then you'll see the Horner-Wadsworth Emmons phosphorus with the oxygens attached used to create the E form, since it's a little bit more selective. Now, since this does a double bond, this is a very useful, not only for carbon-carbon bond forming reaction, but then to figure out how to synthesize these and create a double bond. So we can think about creating something like this, and then that means that over here we'll have 2 parts, right? We'll have the Wittig and the ketone or aldehyde. Now, if we look at that, we could have this ketone with this ylid, right? Or we could have this Wittig, right, plus this aldehyde. So we've got 2 possibilities here from the Wittig. Now, the one of these that favors, we have to remember, we have to think about how we make our ylids, and we make our ylids by taking, I might as well go back to black. We take our alkyl halide, that reacts in an SN2 style reaction. So this comes in, attacks there, kicks that off. we end up with this ion. And then if we react this with butyl lithium, we get the base. So if we're thinking about the fact that this part right here is an SN2 reaction, then if we go back up here, the first one, this would have formed from a primary, but in the second one, this one would form from a secondary. So this would be the reagent mixtures that would be favored. And it has to do with the fact that we get the ylid reaction in the first step. So let's try a couple. All right, so let's take a little time on that. Again, if you're watching this, just go ahead and pause it and you can try it and then come back when you got it done. If we look at the first one, this is a normal way to show an ylid, but it might help if you go ahead and draw this out and show it this way. Okay. What that means then is if we think about this bond, right, I'm going to take and I'm going to connect the two carbon halves, right? So connecting the two carbon halves, right, this comes out that this is pretty straightforward then, right? I have that hydrogen, the CH3, right? So the ylid's somewhat complex. In this case, do I have to worry about stereo centers? No, because I have a symmetric ketone. So it's not going to have an E or a Z form. On the second one, we're just inverting this. So we're starting with the alkyl halide. The first step is to form the phosphorus. So we get an SN2 style reaction. And then we'll add the base. All right, so we get nucleophilic attack, and then we add our base. The base makes the anion there. And then what we add, and here again, it's good if you draw it out. So I've got an aldehyde, that's what the CHO is, that's an aldehyde, and 3 carbons. So when I add those two together, remember, I'm going to make a double bond where the carbonyl is. And oops, in this case, I do have stereochemistry, and I've drawn the wrong one. So in this case, it's unstabilized, so I'm going to get the Z form. All right, questions? Next section we're going to look at is the Baeyer-Villiger. Normally, if we take a ketone and we try to oxidize it, we're not going to get, we're going to get no reaction, right? So if we think about our normal oxidations. And if we think about our aldehydes, right? If we added our normal oxidants, such as, the chromic acid or the sodium dichromate, right? Or potassium manganate, right? These will all oxidize to the carboxylic acid. With the Baeyer-Villiger, what it does is it allows us to oxidize both ketones and aldehydes by insertion, a little bit different, an insertion of an oxygen. So if we look at what's happening, right, I'm actually inserting the oxygen into that bond. The way this works is that we have, again, a nucleophilic attack, but now we've got this peroxy acid. So we've got our hydrogen, lone pair, oxygen, lone pair, carbonyl. This nucleophile reacts here, kicks off our pi bond. Then we get a proton transfer. Turns out this 5-membered ring is fine for an internal proton transfer. So this proton moves there. You can see that it's in a convenient location. Okay, and then we get kind of a cascade. These electrons are going to come down here. This bond is going to break and go towards the oxygen. Right? So this is where we get the migration. These bonds that are between the two oxygens goes towards the carbonyl, and then I get the movement of the electrons there. So what happens is I get the carbonyl, oxygen, methyl, plus then bond. It might help if I colorize these. So let's put, that one's going to be orange, right? It stays orange, and then it comes back as the carbonyl. Then if we go and let's use this green, this green oxygen here then becomes the one that's attached to that carbonyl carbon. And then it's the one that's here in my ester. Right? That's what this structure is here. This is an ester. Then if we look at, let's pick pink, this one's my pink, right? Here it is up here, right there. And then it's the one that ends up being the carbonyl there. And let's go with brown. And then this one over here on the side, it gets protonated in the second step, and then it's the one that ends up being the OH of the carboxylic acid. So the Baeyer-Villiger can cleave a carbon-carbon bond, right? So some classic examples, we can start with a 5-membered ring, right? Add something like MCPBA is a peroxy acid, right? We use peroxy acids to make epoxides. Right, and now what I've done is I've expanded that bond. Okay, in this case, that's symmetric, but what if we had one that's not symmetric? So if we look at this one, we take our our peroxy acid. In this case, it's going to favor migration to the secondary side. So the migration pattern is going to be hydrogen. So if I do have an aldehyde, that's going to be the first one that moves. So if I do have an aldehyde, I can use Baeyer-Villiger to make carboxylic acid. And then tertiary, secondary, and this has to do with the fact that you're going through a partially positive species or partially positive migration step. So tertiary, secondary, then primary, right? And then methyl. So when I have a non-symmetric, I need to know this group. So let's try some of these. Okay, let's take some time. If you want to pause now, that'd be good. Try to answer these. Assuming you pause, we'll go ahead and move on. So here again, on this side, we have a primary position. You want to think about that way. On this side, we have a secondary position. So when we do our migration, we're going to migrate the secondary, right? So this is going to be our major product. On the second one, don't let the CF3 throw you off. What you're looking for is the peroxy acid for the Baeyer-Villiger. And then in this case, we've got a secondary, but we have a hydrogen. So it's the hydrogen that's going to get shifted. So this aldehyde is going to go to the carboxylic acid. Now we've done a lot of reactions so far. So now what we're going to do is look at synthetic strategies. I'm going to start this, but then really the synthetic strategies works best if we do a lot of synthesis, and the best way to do that is in a live class. So we'll do that on Tuesday. But a few things we need to think about with synthetic strategies. You know, a couple of questions. You know, is there a change in the carbon skeleton? Right, and we've already seen in this chapter, we saw several more carbon-carbon bond forming reactions and a bond cleaving reactions with the one we just looked at with the Baeyer-Villiger. Right? And then two, is there any functional group? So often we are focusing on functional group changes, right? So usually that's the thing that we're focused on, right? But we need to think about these two questions and think about how we can get those done. Usually the carbon chain skeleton is going to dictate what's going on in more detail. So what I would suggest doing is going through your reactions. And if you've been making flashcards, you know, on your flashcards, make a note, right? And you can do like asterisks for functional group change, for skeleton, carbon skeleton change. And let's say you could do star, whichever symbols you want for functional group. Some are going to have both, right? So if we think about a simple SN1 style reaction, let's say that we look at dehydration reaction, right? This is going to be both a carbon skeleton change, right? Because we've changed our carbon skeleton because of the carbocation rearrangement. And this is going to be a functional group change, right? Because we've gone from the alcohol to the alkene. But there's other examples, right? Where if we took one of the ones we learned on Tuesday, or what's a review, but sodium borohydride here and methanol going to the alcohol, the secondary alcohol here, right? This is only going to be a functional group change, right? We're going from a ketone to a secondary alcohol. Okay. So look at your reactions, go through them, and see what you can find as far as those different things. We'll continue on synthetic strategies, work all the way through those, do several problems around those on Tuesday. So remember, we got a homework assignment due, and make sure you add these reactions to your flashcards. Have a good day.